Hi, this is Susie Oliver. We're doing an overview for Chapter 1. Here's what our index looks like for the book. We have pseudocode, abstract data types, model for abstract data types, ADT means abstract data type, implementations, generic code for that, algorithm efficiency, and then it's always got key term summary and practice sets at the end. Of all of these right now, algorithm efficiency, which is measured in big O notation, is the most important. All of these others will be hit on again later. Let's go ahead and take a look at pseudocode. Pseudocode is an English-like representation of algorithm logic. It's part English and part structured code. There are no exact rules for pseudocoding. Some people mix the actual language statements in with English statements, and that's fine. It's a lot like when you're writing an essay or writing a novel. You don't want to stop and figure out all of the grammar and the spelling and all that while you're trying to think up the story and get it all down. So that's kind of what pseudocoding is. The idea is you get the general algorithm on paper or possibly on your computer to get the idea of what's happening. And then you start revising it from there, and at a certain point, once you revise it again, it turns into code. Now here they've got an example of pseudocode. This algorithm reads a file and prints a report. So they're going to do loop while it's not the end of the file. Okay? And then, so they don't know yet if they're going to do a while or a for or whatever. It's just a loop. And then they're going to read the file. And then, now if they wanted to say scanf at this point or something, that'd be fine. But in actual pseudocode, you don't usually get to that point. But you can if you really want to. Like I said, there are no rules. Then, if it's a full page, then increment the page number. Write the page heading, and then end if. Now, I don't ever bother saying end if. Again, there aren't any rules. Main thing is you indent or show where your block begins and ends. I actually will use the curly brace to show beginning and end, usually when I'm pseudocoding. If you're going to do it in Python, it might be a good idea not to do that, because then you'd be tempted to copy it in once you start actually coding. Then write report line, increment the line count, and end the loop. Okay? And then you're going to return the line count. Okay, so that's a good generic type of pseudocode. It's a good idea to include a purpose and a return, but again, it's just to get your ideas on paper, so you don't absolutely have to have those things. They put statement numbers in theirs. You do not have to put numbers on your lines. Okay, when you're using variables, you should always use good names. Something that describes the meaning of the data. Don't use things like count or sum or total or something like that unless it's extremely obvious what you're doing. They even go so far as to say don't use single letter variable names. Well, no, that's not true. I mean, I is used all the time in loop control variables and things like that. If you have a short loop and it's going to be a subscript for your array, everybody knows that. So using I in that situation is okay. If you have a three-dimensional array, using I, J, and K are common, and they are acceptable. If you're using an XY coordinate system, using X and Y is okay. In general, don't call a variable X, because that could be anything, right? But if you are using X and Y coordinate systems, and that's obvious, or you've made a comment to that effect, then that's fine. But in general, they're right. Don't use single character names. I use full words and either separate those by an underscore or use camel case, where every full word starts with a capital letter and all the other letters are lowercase. Normally in C and C++ both, you usually have your variable name start with a lowercase letter. And then if you have a second word in it, then you capitalize that one. If you have a third word in it, you capitalize that one, and so on. Okay, statement constructs. There are several types of statement constructs. One is a sequence. Sequence is just a plain old individual line of code. So like a scanf or a printf statement is a sequence statement. Or if you're going to add one to something, that's a sequence statement. Selection statement is where you've got to evaluate a condition, and if it's one way, you're going to do one thing. If it's another way, you might do something else. So if you have the word if, that's a condition statement. If statements may or may not have an else part, but if it does, that's still part of the selection statement. Then you have loops, and loops iterate on a block of code. You go through everything in that block more than one time usually. So a while statement, a for statement. If your language has a repeat until statement, that would be included as well. Okay, here they've got a pseudocode for going through an array. So you're going to loop until not the end of a file, read the number into the array, add the number to total, increment count, set average to total divided by count. And notice they're not checking for 0 here at this point. And once you get past the initial stage, you should check and make sure count's not 0. And then print average, loop while not end of array, set dev from av to array element minus average, so that's deviation from the average, and then print array element and dev from av. I don't like this dev from av. I really would call that deviation or difference from average. And I wouldn't call AVE. Everybody that I know of abbreviates that as AVG instead of AVE. And I would probably use the whole words. I'd say average deviation or something like that. Or deviation from average would be better. Oops. Okay, abstract data type. Atomic data consists of a single piece of information, like a variable. Like, let's say we've got a variable named X. And in the examples, I will call them X, because they don't mean anything in the examples. So if you've got an integer X, that's an atomic data. It's also known as a scalar. It's an individual thing. The opposite of that is composite data. It can be broken out into subfields. So if you've got like an employee, and the employee has a first name and a last name and an address and so forth, that's composite data. If we're working with an object-oriented language, that would be a class. In C, we don't have objects and classes. We do have structs though, and so the struct would be a composite data, and each field within it, the fields themselves are usually atomic. Although you could have another struct within that. Data type has a set of data and operations that can be performed on the data. So if we have integer type, we can do multiplication, addition, division, mod arithmetic, and so forth. For characters, we can check and see if they're less than or greater than each other, that kind of thing. We can do that for integers and floating points as well, although they didn't put that up there. Okay, a data structure is an aggregation of atomic and composite data into a set with defined relationships. In this definition, structure means a set of rules that holds the data together. In other words, if we take a combination of data and fit them into a structure that we can define its relating rules, we've made a data structure. Data structures can be nested, so you can have data structures within other data structures. So everything is a data structure, actually. A single variable, a scalar, that's a data structure. An array is a data structure. That's usually the simplest of what we usually talk about as a data structure. A struct is a data structure. It has fields within it, and those fields in turn might have other fields, and those fields might include an array. And as we'll see, we have much more complex data structures available to us as well, things like linked lists, trees, and so forth. Okay, abstract data types, ADT. I had never heard the term ADT until I got this book, so I'm not sure how widespread it is. I don't think that in itself is a very well-known term. But within the book, an abstract data type is, it has a data structure, it has a set of operations that can be used to read that. When it says a character here, it doesn't mean like a character like ABC. It means it has a purpose, a way of being. With an ADT, the end user, when it means user, it means end user, is not concerned with how the task is done, but rather what it can do. This is kind of like object-oriented programming with the privacy. We know what a data type can do, and how it's done is hidden. When a user sits down to run something to enter a new employee or give all the employees a raise, they don't care about the code, they don't care what data structures used and all that kind of stuff. It's kind of like if you drive a car, you don't need to know exactly how it works. Okay, all this stuff about the data operations encapsulation, I'm not real concerned about that at this point. Just make sure you go through this and get the definitions. For the remainder of the chapter, I'm going to split that up into two more parts. ADT implementations starts talking about pointers and nodes and things like that. So I'm going to do another video on pointers themselves, and then I'll go over section 1.4 on ADT implementations, and then I'm going to make a separate video about algorithm efficiency and big O notation.